We've talked a lot about computational complexity, about how theoretical computer science thinks about the complexity of solving different problems. But of course, in the back of your mind, you should be thinking about, is this the right picture for the field of science that I'm most interested in? Is this the right lens through which to see the complexity of biological systems or social systems? And there are some interesting gaps, or bridges to cross, at least, between how computer scientists think about problems and how we think about them in other scientific fields. So in fact, there are some gaps, or at least bridges to cross, between how computer scientists think about the difficulty of a problem and how you might think about it in other scientific fields. In particular, when computer scientists say that a problem is hard, for instance, that it's NP-complete, this is a worst-case notion of hardness. What do we mean by that? Well, remember when we proved that graph 3 coloring is hard because we showed how to reduce to it from a SAT formula. We showed how to design a particularly hard example of the graph coloring problem by deliberately forcing it to encode tricky logical relationships between Boolean variables. Well, of course, to the extent that we ever run across graphs in the real world that we desperately need to color, it's not clear that the typical graph is hard to color at all. In other words, we're assuming, when we say that this is hard, that the example that we're going to face is designed by a clever adversary to be as hard as possible. It's a kind of pessimistic view of the world and the problems that we might encounter. Now, why is that the view? Well, there are sort of two reasons for this. One is that the standard view in computer science is that if I tell you I have an algorithm which will solve your problem, I want to guarantee that that algorithm will always work. That means it will work on whatever example you throw at it. And in particular, it means even if you do your worst and cook up an example which is extremely diabolical, my algorithm still has to work. It has to face those worst case examples. I also think this has to do with the cultural history of computer science. The fact that computer science really came of age in World War II, when people like Alan Turing were doing cryptography and breaking the Nazis' Enigma code. And of course, in cryptography, you really are up against an adversary who is trying to pose hard problems for you, who is trying to break your codes and come up with codes that you cannot break. But for instance, I was actually raised as a physicist. And in physics, we have a much more benevolent, optimistic point of view about the problems that nature is going to face us with. You've probably heard physicists say that in many cases, when a problem comes to us from nature, the right answer turns out to be the simplest, most beautiful answer. For instance, Paul Dirac found that the simplest equation, which includes the electron as a solution, also includes its antiparticle, the positron. And lo and behold, 4 years later, it shows up in the lab. Or even general relativity. In some sense, it's the simplest possible theory in which mass and energy could cause curvature of space-time. So physicists think about problems in this very optimistic way. Computer scientists tend to think in a rather pessimistic way. And I think it's an interesting question whether the problems that are posed to us as scientists in the social sciences or the life sciences, are they the kind where often the right answer is a very simple one? Or in fact, is it often very complicated and messy and hard for us humans to figure out? Since I'm not an expert in those areas, I'll leave that to you to decide. But anyway, you should be thinking about, gee, is this the right attitude? Is this the right lens through which to think about or see the complexity of the problems that I'm going to have to deal with in the systems that I study? There is a beautiful quote in Norbert Wiener's book, Cybernetics, which, by the way, is still really worth reading. He asks, what kind of devil is the scientist faced with? Is it a Manichaean devil or an Augustinian devil? So these are nice old theological terms. The Manichaean devil is really trying to screw us up. The Manichaean devil is trying to deceive us. It's going to cook up those complicated examples that lead us in the wrong direction. Whereas the Augustinian devil is more just the devil of disorder, of entropy, of a lack of knowledge. And in that case, we're not up against a malevolent force. We just need to learn more and look at things more closely. So anyway, a little philosophy for you there. Now, in fact, it's a truism, a common experience in the real world of solving computational problems, that even when a problem is NP-complete, or even worse, in the worst case, it's often quite easy in practice. And many algorithms or problems that take exponential time to solve, if you cook up a diabolical example of them, you find the naturally occurring examples and you can deal with them quite easily. Here's a classic case of this. Earlier on in the course, we briefly mentioned this class of problems called linear programming problems. This is a large class of optimization problems that, for instance, it includes the max flow and min cut problems. We have a bunch of variables. We have constraints on these variables, which are linear inequalities. So something plus this plus something, something times this plus something else times that minus something else times that has to be less than or equal to some constant. These are popular in economics, for instance, where you're running a bakery and your chocolate chips cost something and your dough costs something and you have a total budget and blah, 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 blah. Now, then there's something you're trying to optimize, maybe your total profit or the total number of chocolate chip cookies you can make, and so on. I personally find these economics examples a little bit boring, so instead I'll tell you that these problems involve climbing up to the top of a high-dimensional jewel. We have this jewel, or a mathematician would say a polytope, like a polyhedron, but in many dimensions instead of 2 or 3. It has these facets, these flat planes or hyperplanes, which are the constraints on our variables, and we're trying to go up as high as we can to find the top corner of this polytope. But especially in high dimensions, there could be many, many facets and corners to this polytope, and so this is a potentially hard problem. Now, there's an old algorithm called the Simplex Algorithm, which goes back to Danzig in the mid-20th century. And it's a simple, greedy algorithm. You kind of start anywhere, and then you climb up, moving along the edges or faces of the polytope, moving from one corner to the next until hopefully you get to the top. Now, there are nasty examples that people made up, where you have something that's almost a cube, but with very slight perturbations to the heights of the corners, so that the simplex algorithm will take a very, very long time going around these corners in a very long tour, each step of which makes some infinitesimal improvement, and so that it takes exponential time to reach the optimum. But people use this algorithm all the time, and in practice, it almost always works really, really quickly. So this is a challenge to theorists. What is it about the typical problem which makes this algorithm work so well on average? And for a while, people struggled to figure out what that means mathematically. What do you mean mathematically by the typical problem? What structure or what statistical properties does it have? So Dan Spielman and Shenghua Teng came up with a lovely explanation for this, a lovely theorem which really does a good job of explaining why this algorithm works well in practice. They said, go ahead and let an adversary design any example they want, as diabolical as they want. Then add some noise. Because of course, in the real world, you never know exactly what the coefficients of your constraints are. You never know exactly what the right-hand side is. In the real world, things are a bit noisy anyway. So take all these parameters of the problem and add a wee bit of noise to them. Spielman and Teng proved that if you do that, then no matter what initial problem you started with, however adversarial it was, this noise with probability tending to 1 makes the polytope much simpler. It greatly reduces the number of vertices on that path from the bottom to the top to a polynomial number, so that the simplex algorithm, or at least one version of it, will find the global optimum very quickly. So this technique is called smoothed analysis, but what it says is, yes, there are hard examples, but they are rare and they are fragile. That's interesting. So yes, the adversary can cook up a nasty example, but it's only nasty if he gets to very carefully fine-tune its parameters. And in fact, any amount of noise will make it fall apart, make its hardness fall apart, and make it much easier. Now that's interesting, because there are other problems where we think the hard cases are in fact common instead of rare, and robust instead of fragile. Think again about cryptography. A secure crypto system is one where it's computationally very hard for an eavesdropper to figure out what secret message you're trying to send to your friend. Well, it's not enough for there to exist hard examples of that problem. I wouldn't be happy buying a crypto system from you if all you could tell me is there exist messages that are hard to decode. I want all the messages I want to send, or at least the vast majority of them, to be hard to decode. So when we talk about NP completeness, we don't pay attention to this. We just say, oh, do there exist hard examples or not? But when you zoom in a little closer, you realize that in some cases those hard examples are rare, and in others they seem to be common. And that's a further distinction we can draw. Let me explain another reason why problems which are hard in the worst case are often easy in practice. And this has to do with the structure of the landscape. So Maria Florina Balkan, Avrin Bloom, and Anupam Gupta had a lovely paper about the clustering problem. What's one of the most basic things that scientists do to analyze their data every day? We have a bunch of points in some high-dimensional space. Maybe each point is a rat, and it's a point in 20-dimensional space corresponding to how active 20 different genes are in the rat. Now, we want to find clusters of these points, maybe corresponding to sick rats and healthy rats. So this is something we're trying to do all the time. Now, in fact, if you define the clustering problem as an optimization problem, finding the best possible clusters so that they minimize some definition of cost, like the total distance or the sum of the squares of the distances from all the points to the center of masses of the clusters you put them in. This is a hard problem, but it's a problem we solve every day. So, again, when I say it's a hard problem, what I mean is there exist hard examples. And why are those examples hard? Well, it's because there's a global optimum to this clustering problem. There is a clustering which is best, but then there are other clusterings that compete with it that are almost as good, they're almost as high, their altitude is almost as high in the landscape, and yet they're very far apart from the optimum. So you have this bumpy landscape with lots of local optima that are almost as good as each other, but which totally don't agree with each other. And so algorithms get stuck and it takes exponential time. But step back for a moment. If your clustering algorithm, where you're looking for, say, 7 clusters in your data, has a bunch of different ways to cluster it that are all roughly equally good, but that totally don't agree with each other about which points belong in which cluster, then maybe you're asking the wrong question about your data in the first place. After all, if there really are 2 or 3 or 7 clusters in your data, well then, there should be a clustering which really dominates the landscape. It should be kind of shouting at you, this is the right answer. And there shouldn't be any other answers which are almost as good, but which are totally different from it. This is interesting because why do we solve optimization problems anyway? If you're trying to design a rocket ship, and one design is a little bit better than another design, even though it's very different, well, you should use the design which is a little bit better. But here we're not designing something. We're trying to find the truth out about our data. We're trying to find a pattern in our data. And I claim that in this case, if the landscape is really bumpy, then the pattern we're looking for maybe isn't really there. So, back to Balkan, Bloom, and Gupta. They said, suppose that the instance in front of you has the following structural property to its landscape of solutions. Suppose that any local optimum, which is almost as good as the global optimum, is also close to the global optimum and agrees with it on most points. In other words, yes, there might be little foothills at the basis of the global optimum, but the global optimum dominates the landscape. You don't have another mountain peak far away, which is almost as high. Under this structural assumption, they showed that a certain clustering algorithm, kind of like the k-means algorithm, which is pretty popular, works very well and works very quickly. So I think that's a lovely kind of result. It says that it's a way of formalizing the structural property of the examples that you might be focused on in the real world. So let me give one other example, last one, of why real-world problems might be easy. Protein folding. What is protein folding? Well, it's a computational problem. I give you a long string of amino acids, the description of a protein, and the question is what conformation, what secondary and tertiary structure where this protein folds up, some of the amino acids link to each other, and it forms a three-dimensional shape, what conformation minimizes the total energy, where the energy is given by the interactions between the nearby amino acids. Well, guess what? This problem, or a kind of suitable digitization or discretization of this problem, is NP hard. Okay, so it's hard. On the other hand, it's a problem that your cells and the machinery of your cells, your ribosomes and so on, are solving constantly all the time. Does this mean that your cellular machinery has some magical ability to solve exponentially hard problems? No, I'm sorry, it doesn't mean that at all. What it means is that you have evolved both the examples of this problem, namely the amino acid sequences of your proteins, and the algorithm for this problem, namely your ribosomes and all this extra stuff, the chaperone proteins and so on that help the folding process work. You have co-evolved the examples and the algorithms so that these examples will be really easy for these algorithms to solve. Because if you got stuck in the wrong conformation in a local optimum, the protein wouldn't work and you would die. So this is a nice example where it's the opposite of an adversary. There's an incentive for you evolutionarily for the examples to be unusually easy instead of unusually hard. And in fact, biologists have found that if you look at the actual energy landscape of real protein folding problems, there is a nice deep bowl. Remember here we're minimizing the energy, so the optimum is a bowl instead of a mountaintop. There's a nice deep bowl surrounding the correct conformation so that the protein folding machinery will naturally slide quickly and easily into that optimum. In fact, biologists have even found that organisms that live at higher temperatures have deeper bowls around the optimum so that thermal noise won't accidentally kick you out of it and cause your proteins to end up in the wrong conformation. So again, if we look at real-world problems in nature, we find there is a powerful structure to the landscape of possible solutions that makes them very different from worst-case problems designed by a diabolical adversary.